Now getting into that, what exactly an improper integral is. Now let me just bring back some problem that we've done right here. Like say an integral like this, 1 over x squared, for example, right? And then from integrating from 1 to 3, okay? We should be able to do this thing easily, right? See what I'm saying now? Okay, we think of that as an x minus 2 powers, right? And then from 1 to 3 right here in dx, right? And then the fundamental theorem of calculus, right? Say you can go to x to the minus 1 power, right? And then it takes that and negative 1 for the antiderivative, right? And then substituting in 1 and 3, or 3 and 1, right? The high value and the low value. And so minus 3 to the negative 1 power, okay? Subtract, right? And then minus 1, right? To the negative 1 power. You guys following? Okay. So that's making it really a negative 1/3, right? And plus a 1. And then the answer comes out being a 2/3. There's no problem. That's what I'm saying, no? That's just simple, right? At least one thing that's I want to remind you, back in the days we learned about the fundamental theorem of calculus right here. I mean, it was there among the theorem was when it was worded, but it's that some detail that back at that time we didn't have to pay attention, but now it matters. You see, the whole reason that we were able to use the fundamental theorem of calculus just fine for this integral, right? Especially on the interval from 1 to 3 right here, that was because the reason we were able to do this, right? That was because at least the function 1 over x squared right here is continuous, okay, on the interval from 1 to 3. See what I'm saying, huh? Right, it was continuous on the interval from 1 to 3. You guys agree on that? Okay? Okay? And that's why, and that was one detail that back in the days of learning about the fundamental theorem of calculus, when we first learned about it, nobody wanted to pay attention to that because we would just want to get into the sweet side of it, right? The one that the more practical side of it, get straight into doing it. But the whole other big reason behind the scene is the function need to be, in order to use the fundamental theorem of calculus, your function need to be continuous inside of that integration interval. That's the idea. Okay. So now I'm pointing out that detail. Let me erase this problem away. So now think about the problem. It's going to completely switch into something else different. I'm going to just go from 1 to some other variable t right here. Okay. So t, of course, t is greater than or equal to 1. Well, I'm saying that, but I'm going to take some interval, some definite interval from 1 to t, and I'm letting t as the limits go to positive infinity. See what I mean? Okay, and that's the idea. So now let me roll down my screen right here, and I want to give that demonstration. So this is algebra for 1 over x squared. And you guys don't have to wait until now to know it, right? And then if you want to verify me again, you can just hop onto Google, right? Or use your decimals the same with what I'm using here, right? And then graph it out, and it's going to tell you the function. So this is the graph for 1 over x squared. The idea now is that I'm going to go from an interval from 1 to 3, from 1 to t, so some t. So here's how it looks. That interval right here, okay? When you go think about the interval, the picture of the interval, when you're integrating that from 1 to t, right? Then you have this blue area. You guys following? We have this blue area. Right? That blue area represents the interval from 1 to t. For this function, 1 over x squared, right? And so now that work I was doing earlier, as we want to take the limits, letting t go to infinity. Right? Well, in my work here, I'm using the variable a right there, right? The variable a right here, but that a represents the t in our work. The idea now is that we're letting a go to infinity. You see what's going on with the area right there? It keeps flowing out, right? So as we drag the t further out, right? As we drag the t further out, we reach more area. See what I'm saying? We reach more area, right? That's the idea right there. Okay? So that's one way. And then there's another kind of problem right there. And then you can kind of see the idea already. So the same function, I can also produce some problem like this. How about I'm going to go from -1, right, to some t right here. And let's not use the same variable. It doesn't have to be the same variable actually. How about some s down here, right? But I'm going to take the limits by letting s approaching negative infinity. See what I mean? Okay. So of course s here is some value that's less than or equal to -1. So and again, think about this first case I introduced. Then we have an interval anywhere that you drag your t out, right? And you got an interval from 1 to t, right? And then yes, 1 over x squared is continuous. It's continuous on that interval. See what I mean? And then the same way over here, when you're looking at this interval, the picture looks like this. You got that graph right here, right? -1 is somewhere here, and you want some s right here, being less than or equal to -1. And then your picture on that left side is kind of like this, right? So this is the accumulation right here from s to -1. But then you want to take s further back to the left-hand side. See what I mean? Right. And so, yes, we produce an interval from s, right, to -1 here. Right. And then, again, 1 over x squared is also continuous on that interval. You know what I'm saying? That? Right. And so, in this way right here, how do we proceed into the problem? How can we get into the problem? So in what I said, I produced two separate problems, right? One problem here, we got an interval, right, where we let t go to infinity, but then in that interval, at least the function is still continuous in that interval. See what I'm saying? Now, so let's take that. So the reason I mentioned about continuity here because we need fundamental calculus eventually, right? So for that first problem right here, the 1 over x squared, right, dx, and we take the integral from 1 to t right here, but letting t as a limit, taking t to infinity. Right? Well, fundamental calculus say we can just take that as a minus x to the -1. You guys follow it? Right? We're evaluating that from 1 to t. And then now on top of that, we have to take this as a limit problem with letting t to infinity. See what I'm saying? Huh? And so in the next step, think about it again. See, even before I put on top of that this limit operation right here, the fundamental theorem of calculus says you can just go minus 1 over t, right, and plus a 1. You guys agree? Right. And then, because that's after substituting t, the upper bound, and 1 being the lower bound into your antiderivative. Okay, but then, now it turns out to be, instead of a finite number, it turns out to be an expression in terms of t, right? And now you take the limits as t goes to infinity. It's similar to the idea of the fundamental theorem of calculus, part 1 with that similar. But now we're taking that in a slightly different approach. You know what I'm saying now? Okay. And so think about we produce an arbitrary finite interval, right? The bottom end, the idea, the generality is the bottom end is a fixed number, it's some fixed number. The upper end is some changing variable, and then we keep letting that go to infinity. You guys got what I'm saying with that? So now, as we let t to infinity, what's going on with this limit here? It comes out being what? X shrink to 0, right? Go to 0. That goes to a constant term 1. Right? So our final answer here is 1. So we do for this function right here. For this problem right here, it's an integral. So you can say that the integral here, 1 to t right here, where you take the limit, t to infinity, right? That's for that function. The actually it equals 1, right? You have a result for this. See what I'm saying now? Okay. So why don't you guys quickly try the other one? The other one was, see that we got from x to -1, the same function, 1 over x squared dx. And we take the limits as as s goes to -infinity at the time. Okay. Take your time trying that out. Make sure you got your steps, because when I'm asking you for some result, I will ask for your steps as well. What's the antiderivative here?
Well, it's just negative x, the negative first power.
Thank you. Okay. And then we're evaluating that from s to -1, right? Take limits. S goes to -infinity. So go ahead and substitute it in, and get me your step where you substitute these in.
Okay, that becomes the limit of s approaching negative infinity
Uh-huh.
of 1 plus 1 over t, 1 over s.
1 plus 1 over s. Okay. You guys agree with that as well? So see, definitely in this style, of course, we're still applying the fundamental theorem of calculus, right, into our interval from s to negative 1, but then, of course, we have to consequently end up with an interval, I mean, an expression, right, in terms of s. And so now taking that limit, allowing s, letting s approaching negative infinity. Go ahead.
I would just end up being 1.
Another 1, right? As that term goes to 0. See what I'm saying? No? Okay, and that's plus 1. Yes, I agree. So that means for this weird integral work, right? From s to negative 1 here. Function x squared dx, right? As we took the limits for letting s approaching negative infinity, right? We came out to the answer being 1 as well. Right? But really, it's not. So it's it's weird at first, but this kind of problem will happen a lot in many applications out there. So now, in that way, here's the thing. We found some 2 results, right? We found 2 results. But what is this kind of work right here? We call that. So back to this problem, we knew that at least the interval, the arbitrary interval from that fixed low end, right? That fixed low end to a changing upper end right here, and that upper end we left limits to infinity. See what I'm saying now? So this setup right here, we define that. We define this interval over here. This is we define that. We define an interval that looks like this, from 1 to infinity. You see what I'm saying now? Right? Instead of writing too much, right? We define all of that whole setup right here as an interval from 1 to infinity. Right? For the function 1 over x squared dx. So this, anytime you see this, now, right, it means, as a definition, it means that the work we do here is on that function 1 over x, right? We produce arbitrary interval from 1 to t right here. See what I mean? Okay. And then do the integral as usual, but then we take the limits as relating t to infinity. See what I'm saying? Now we define. So this is, ladies and gentlemen, this is one improper integral over here. Right? This is what's so-called an improper integral, right? Where your upper end right here is infinite upper end. See what I'm saying? That. Okay. And so guess what? What do you say about this other problem right there? The other problem that you guys just finished. You see, we go from an arbitrary low end, right, to some fixed upper end like that, right? And then yes, in that interval from s to negative 1, your function is a continuous. I mean, the function itself overall throughout the entire domain is not continuous. It's discontinuous at 0. But right now we're only focusing on that interval from s to negative 1. And then we're letting s keep getting further to the left-hand side, right? So the function is for sure continuous on that interval. Am I correct? Okay. So in that way right here, see, we also define, we have, on the other hand, we have another style of the interval, another definition right here. An interval like this, we can define minus infinity to minus 1. See what I'm saying now? It's another improper interval where the low end is negative infinity. And then this is, for that function, 1 over x squared dx, right? And that's the way what it means here, it represents, that's what the equal sign is for, it represents it's a limit work, right? It's a limit work where we're letting s to negative infinity, right? From s to negative 1 on this function specifically. Yes. You guys with me on that so far? Right? And so now that gave rise to, that promotes, right? For the work that we're doing right now, it promotes to special forms, right? To special subforms of an improper integral. So now after you guys finish writing this down, I'm going to have to erase out that board. I need to still keep the other side there. So as far as a definition, Now we got 2 separate ones right here, right? So we define the improper integral It's like this, from a fixed value to infinity, right? On some function f of x dx. Right? The proper integral like that, right, is defined. This is a defined value. Right? It's defined as the limit work for a to some arbitrary t. Right? Take the limits t equals to infinity. Like your function f of x dx. That's the first thing. We define this improper integral to be that limit work. Okay? Provided the limits exist. Okay. Exist, and I mean in open parentheses as a finite number. Okay. Further, where f of x, right, is continuous on the interval from a to t. Okay. So that's one of them. That's that style right there. And then the other style, in part B right here, the improper integral. Another one, right? Improper integral. That's in the form of a minus infinity to some number a being fixed, right? Of a function f of x. Yeah. It's the same as the limit work. Taking some s to negative infinity. When you go s to a, yes, divided s to a, right? So that introduces two separate forms of an improper integral, right? So generally, it's what I see it as one class of improper integrals where one end of the integral is fixed, right? And then the other end is an infinite end like that. See what I mean? Okay. This definition gives access. It's not only just a definition, but it gives us the way. So anytime you see this notation, right, it means this is how we're doing this. See what I'm saying? Or it represents this kind of work. Okay, so this is just a symbol that represents this kind of work. Am I being clear with that? Okay. All right. Right, so we got to the definitions of what it means by these two integrals, these two improper integrals, right? We've got two slightly different situations there. And then this equal sign here really means that it's a definition we define, right? We define the way of doing this improper integral where the lower end is definite and the upper end is an infinity right there. We define that integral to be the limit work, right? So the limit work is the answer to that improper integral. And then similarly, we have this other improper integral over here where the left end, the bottom end is a negative infinity, and the upper end is a finite fixed number. And so that is the definition. We define this integral to be that limits, right? So you guys have seen some of that action. And so let's do some actual example now. We're gonna do quite a few examples, and throughout the examples, I'm gonna come back to that the definition and fill in some more terminology. But let's now call that example 1. Just a simple evaluating example. You want to evaluate. Okay. So the first integral, the first improper integral we have here. How about okay. Yes, have that. Go ahead, have that written down. All right. And so in the way how it is, the function is here, right? And then this function e to the x, e to the minus 5x. Clearly, it's a continuous function. The graph from learning from your pre-calculus days is going to be something like that, right? I don't have to get anywhere too precise with that. But at least the interval that we do here, so by definition, right, this integration, this improper integral over here is defined to be, first we're going to produce an integral where we go with that fixed 0, right, to some arbitrary t value there. So think about from 0 to t. So at least I mentioned earlier that this function is continuous on the whole real line, right? So in this interval from 0 to t, it should be continuous in there as well. And so we can produce that integral for e to the minus 5x dx. But then the work here is that once you've done with the antiderivative and do the fundamental theorem of calculus, we have to, on top of that, take the limits as t approaching positive infinity. Okay? And so that's the starting step, and that makes it right out from the definition. Now I'm going to take the graph away. All right, so in the next step, it's just a matter of, I'm going to come down here. That's a limit work, but we're holding on to the limit work like, until like pretty much the very end here. But antiderivative of e to the minus x, right? At this point, the indefinite integral that you have done that quite a few times, so it's going to be a minus 1/5 e to the minus 5x. 5x. And we're going to evaluate this from 0 to t. We have been learning that from the fundamental theorem of calculus. Any questions for me on that so far? And so that will take me to the next step. So once again, the limits, right there, but we're not really doing that yet, right? Limits to positive infinity. So we're going to go minus 1/5 e to the minus 5t. We're subtracting is 0, substituting in, and we got a minus 1/5 here, so that really becomes a, or how about just like that? Negative 1/5 again, right? E to the minus 5, 0. Sticking with parentheses pretty closely with that. So in this way, just like the earlier demonstration example, now this is a plus, right? So I have a function in terms of t here. At this point, I have an expression that depends on t minus 1/5 e to the minus 5t, right? Plus the 1/5, right? But then all of that here is just e to the 0 power is just 1, right? So we have our expression in terms of t. Now we take this limit t to infinity. So you guys can quickly see that this constant will stay the same, right? The minus 1/5 times e to the negative 5t right here. Well, we can, to optionally assist your understanding, it's the same. E to the minus 5t is the same as a 1 over e to the 5t. So now as t gets large, right? As t gets larger, from calculus 1 right here, we can see that as t gets large, this denominator will get large, right? But don't substitute the infinity in there. Okay? I keep seeing some students here and there doing that. Well, not here anymore, but I keep seeing that elsewhere doing that. And so as t gets large, the whole denominator gets large, so the overall goes to 0, just like how we've been knowing it since calculus 1, right? So in this way right here, that first term becomes a 0, right? Now it plus 1/5 here. So our final answer comes out in a 1/5. Now, as a final conclusion, see, upon this limits work here, we came to a final answer being 1/5. So I can say that this improper integral we have from the beginning, 0 to infinity, right? This improper integral has an answer equals 5. I mean 1/5. Right? And so right here, after that example right here, after this part A of the example, you can see that this limit, so the answer to any kind of improper integral this way is definitely a limit work, right? The answer to a limit work. Okay. So now when you're seeing this value right here, it's an answer that came out from a limit work. So now that tells me that this limit work now is a convergent limit work here. So you're saying that here's a new terminology. That integral, this improper integral is a convergence, okay? So, formally as a statement, you're saying that this improper integral as one entity, really, as one object, right? This improper integral is convergent. That's how we're saying it. Okay? So it's a new term that we bring in. So anytime the integral, the improper integral, right, comes to a finite limit, right, comes to a finite answer, we call it a convergent integral. Any questions? So in that way, let me look at another one. Minus infinity to 0. Other form, 1 plus x squared 2x. We have another improper integral. So again, just like that. This improper integral means really we are doing the integral from some s, some arbitrary s, right? To 0 over here. Or you can also call it t, but keep in mind the idea is the bottom limits here goes to negative infinity this time. Limits for s approaching negative infinity. You want function of 1 over 1 plus x squared dx. Okay. I can quickly show you. I mean, this one here should also be mentioned once or twice in your pre-calculus courses, but in case it was not mentioned, it's completely okay. Let me bring down the picture over here. This is the graph. That's the graph for your 1 over 1 plus x squared. Right? And so obviously from the graph, that it's a continuous function. Right? And then we can also algebraically proving it. So from count 1 understanding, we can easily prove it. But that's not the big goal of the problem right there. So proving continuity of this function, so we can just leave that for sort of like side work again. All right. So now the point I'm mentioning about continuity, and you saw that earlier on the graph, it's continuous throughout the whole real line. So at least in this interval right here from F9 symmetric interval here, so from some s right here to 0, your function is at least continuous in that interval. Now I am going to continue further with that limit work here. So it's a little bit work. We'll be letting s approaching negative infinity, but what is the antiderivative of 1 plus 1 over 1 plus x squared? Anyone remember? Tangent inverse. Tangent inverse. Okay? The arctangent or tangent inverse of x. That's right. So now we're going to evaluate that from 0 as the low. S is the low, 0 as the high. So, we look at that still. And so the work here will, yes, as usual, we're going to have tangent inverse of 0 minus tangent inverse of the s. Right? And then here we're definitely looking at an expression in terms of s right here. And tangent inverse of 0, by the way, is anyone know? What angle gives you the tangent value being 0? So this 0 right here is the tangent 0. Tangent value, right? So what angle would tangent inverse mean? We want to get the angle. What angle gives you tangent value equal 0?
I guess you could just arctan 0 into a calculator and you get it.
Well, yeah, you can use the calculator, but at some point, what if you don't always have the calculator? Anyone remember? Just the 0 angle as well. 0 angle. All right. So, and it's a little bit worse. So now, yes, it goes to that term is 0. So really, we just have it's a limit. One more time. Limit for s was approaching negative infinity, but minus tangent of -1. Yes. There you go. Okay. So another reminder for everyone that the graph for tangent and tangent inverse. So ladies and gentlemen, the tangent inverse is this function like that. Like it has that shape, and I can zoom it out a little bit more. That's the tangent inverse. So it really has that asymptotic behavior here actually. So this is some property that we should have known from the calculus, from pre-calculus 2 to your trigonometry courses. Y equals a pi over 2 is the upper. You see that line like that? That's the upper vertical, horizontal asymptote. And we have another, we have a lower horizontal asymptote as well. That's the one on the bottom. See what I'm saying? So, but that's the ordinary tangent inverse. The function we're looking at here is indeed negative, right? So I'm just going to simply put it in a negative sign right here. And let's investigate the graph. It goes like that. See what I mean? So now we want s to go to the negative infinity, right? We want s approaching. So think about a variable. We want the variable approaches negative infinity, right? So it looks like the vertical values come as high as, keep trying to make it ways to reach a positive pi over 2, right? See what I'm saying now? So that's coming out from the graph result. So some of these basic graphs from your previous courses, make sure you guys get some good review of those. Right, but that means now I'm ready to say that my answer here comes out for this limit, right? It comes out being a positive pi over 2. We're good with that still, right? Because of that graph of your function again. And so now you can make that final conclusion, right? So it's the integral, the improper integral from minus infinity to 0 over here on this function is 1 over 1 plus x squared, right? This is a pi over 2. We found some answer. And once again, the answer here turns out to be, because remember, this answer is not really equal, because there's no such thing as this thing just means, right? It's just a representation of a limit work. That's what I'm saying. So this limit work came out being a finite value, right? So you're saying that your integral here in the terminology I just introduced, right, is convergent. Your integral is convergent. Yeah, no? Right? And then so, we've seen 2 problems so far, and they're all convergent so far. And so, let's continue into another one. I want to give you guys a few different scenarios here. Call it part C of the example. Natural log of x over x. Yeah. So, again, just getting comfortable with the setting up here. So this just means, right? It just means it's a limit work here that we're taking the limits for t goes to infinity, positive infinity, right? But then on top of an infinite, a definite integral from 2 to some arbitrary t. Natural log of x over x dx. Right? That's the setting up for that problem there. So now, in that way of how I'm seeing it, then, well, the fundamental theorem of calculus, but with this one right here, we've got to apply some technique that we've learned previously in the quarter, right? So we can bring back the u substitution method that we've learned earlier. I'm going to let u equal natural log of x, right? And so letting u equal natural log of x, you can further see that the du dx, right, will equal to 1 over x, or even a little further, right? Can rearrange the differential, making it du equals 1 over x dx. And so 1 over x dx will be dx over x, or 1. You can see this x in the denominator together with that. The dx here is the same as 1 over x dx, right? So I'm getting ready for that substitution later on. But now further, right now, aside from looking at this as a limit problem, right? You can see this basically as a definite integral, right? You got an upper end being t, right? And the lower end being a 2 over here. So doing this u substitution, why don't we also go u1 for the lower here being natural log of 2, because we substitute in that bottom end, right? And then the u2, the higher here, right? You're gonna substitute t in your function. Sounds good? So keep in mind, right now we are pretending that t is some arbitrary finite stop, right? Some finite value. It's a number, it's a numerical value. So now the integral becomes something like this. It's still a limit problem where t goes to infinity, right? But your integral here will become the u1 right here is a natural log of 2. Are we good? Okay. The upper end now becomes a natural log of t, right? And your integral here we have, so natural log of x was substituted by u, so we got u right here. And then let's separate out this whole thing right here is the same as natural log of x, right, times the 1 over x dx that I mentioned earlier. Right? So that means the integral here will become just all of that part right here is now a du. See how nice thing turns out? Okay? So in that way, yes, fundamental theorem of calculus will come in, right? We have 1/2 u squared, right? Then we're evaluating from natural log of 2 as being the low, right? And then natural log of t being the high. And then of course this problem remains permanently as a limit problem where we're taking t approaching positive infinity. So in that way right here, in my next step, right, I'm looking at, well, we're just evaluating it, and I'm still holding on to the limits problem right here. We're looking at the 1/2, right? Now, substituting natural log of t into this u right here, we're we're now looking at natural log of t all squared, right? Natural log of t all squared. So it's a square of a natural log function, not the natural log of t squared. Okay? It's a square of your natural log function minus 1/2, right? Natural log of 2 all squared. Now we can realize that this is completely a constant, right? This particular term right here is simply just a constant. So that only variable, that only expression in terms of t is here, right? The one that we can determine the value differently depends on the t value, and we're letting t approaching positive infinity, right? And so now think about it. I'm going to put on the graph again. All right, so our natural log of x function is right here. You guys all follow me on that? Okay? So the natural log function is just simply rising and rising, right? Even though it's rising slowly, right? You can see that it's not going like rapidly up. It's rising slowly, but in the end, it has been only just rising. You know what I'm saying now? And then so further out, but our actual function here is the natural log of x. It's a 1/2. Okay, natural log of x, and even further square. See how quickly that rises right there. Okay. All right, and so in that way right here, that means what? My point now is that as we let the variable approaches positive infinity, right? Then our overall 1/2 natural log of x or natural log of t or whatever, right? All squared is going to rise to positive infinity, and then knowing that now rising to positive infinity, and then on the other hand, this other term stays constant, right? So the overall limit here goes to what? Now you can tell, right? It has a right-hand behavior being positive infinity. See what I'm saying? No? Okay. And so again, there's back into calculus 1. What we learned about this, I mentioned clearly. There's no such really a concept as equal infinity, but we write equal infinity just to simply indicate that the limit work right here turns out is an infinite value right there. But there's no such concept really as a some number equals infinity. Okay? Because infinity itself is not a number. But then because we adopt that convention that hey, the limit work here turns out to be infinity. Now we can also say that our beginning improper integral, right? Okay. We'll have answers, right? We'll have answer being infinity. Okay. So writing equal sign, but it doesn't really mean a numerical calculation or anything like that. Okay? It just means that the limit what turns out and it came out being a negative, being an infinity. Okay? But then I've been using the term convergence and all that so far because the earlier problems in our example here showed the limit, the final limit came to a finite stop, right? It came to a finite value. But in this case right here, indeed, the integral came out being infinity. And so now I can tell the new terminology here is we're saying that the integral is divergent. Right? That's the term, divergent. Right? So, or another way of stating it, this integral of 2 infinity natural log of x over x, right? dx. This integral is divergent. You know what I'm saying? No? So it's divergent any time the overall limits comes to a like infinity, or sometimes it does not exist. Okay? Remember back limits right there. I myself I see the infinity or negative infinity as some limit. It's just the infinite limits, right? But sometimes the limit itself may turn into like one way is going like this, the other way going like that, right? Remember that from count 1 right there? Okay. So the limit word can sometimes turn into a D and E, like it does not exist. Right? And so when it does not exist, you also say that your integral, your improper integral, is divergent. You know what I'm saying? No? It doesn't have a finite stop. Right? All right. And so let's look at another problem here. Just want you guys, and along with these problems here, we set ourselves into a good routine of how we do these improper integrals. Minus infinity minus 1 over our cube root of x dx. Right? Again, we're thinking about this problem here, right? The equals to have negative 1, right? S, right? As being low, we get negative 1. The negative 1 is the upper end. S is some lower end, right? Of your integral. Your integral here, your function is 1 over cube root of x dx. now we want to take the limits, right? As s goes to negative infinity. So the integral really means that this limit work. Okay? It's not like we produce the limit work to do the work, okay? To do the integral. It means it is that the limit work that we are doing. We write that as this improper integral. So now on this limit work right here, once again, you can think of that. Well, I just go ahead and write the limit notation right here with one more step. Here. Seeing that as a x to the negative 1/3 power, right? That cube root in the denominator is a negative. I mean, is a 1/3 power, but then in the denominator it means it's a negative. Right? Cube root is a 1/3 power, and then we get in the denominator, it brings that into a altogether it's actually a negative 1/3 power. So now we can, and with something like this, we don't have to do any special substitution or anything like that, right? Yeah. With the antiderivative can come out quite simply, quite easily. So it's a little bit work. Then our antiderivative here is a positive 2/3, and then we add it, so we're dividing that, so it's 3/2, right? So times x to the positive 2/3, it's adding 1 to that. And then we're evaluating from s to negative 1. And keep in mind that it's an odd root, right? So that means the negative number is a completely okay, right? That's just a brief algebra reminder for anyone. So that's why it's completely okay to, it's entirely okay to substitute negative 1 into your 2/3 square root. Okay. Right? Now, it's a little bit work. Well, maybe I should write it in the next line down below here. A little bit work. Then s approach negative infinity. The 3/2, right, times negative 1 to the 2/3 power, right? And we're subtracting 3/2 times s to the 2/3 power. So I don't even need to actually evaluate this, right? Well, it will come out just 3/2. See what I'm saying? Yes, but my point is that we don't even need to do that evaluation because the whole expression here is an expression in such as, and this is the only term that matters, right? The term that stays behind that subtraction sign effect, right? That's the only term that matters. So now as s goes to negative infinity, think about your 2/3 root function. You don't see this too often, but in these days, we got quite a few good number of resources for technology. So let's use the graph again. And Decimal is just one of the choices out there. We don't have to always use Decimal, but you can use your favorite one as well. I have a 3/2 here, x to the 2/3 power. Okay. Let me show the graph here. It looks really a graph that we've never had to see that before, but now the graphing utility can easily get us there, right? But now we want, and it's negative, okay? So let me put that in the negative side of that. Okay. Going to our work. See what I mean? So now as s goes to negative infinity, so thinking about we're heading to the left of your graph, right? And so now the graph here shows what? It shows the vertical value keeps dropping further down to negative infinity. All right, so that's how we argue about that. So in that case, we have an answer to this. It's negative infinity, right? The answer to this limit is negative infinity. So that means our definite integral, this definite integral here, x dx, has an answer being minus infinity. Okay. So you can write it that, and then you can also say this is another case where I was pointing that out, right? That your integral here is divergent. A divergent integral, or we're saying that's this integral of minus infinity minus 1 here over cube root of x. I mean cube root of x dx is divergent. got a limit that's heading to negative infinity, so the integral itself is divergent. I mean, in some strict classical setting, back at the old days, you weren't even allowed to write equals in infinity like that. You just say, hey, when that limit comes to a negative infinity or some infinity, you just say the integral is divergent. Some teachers back then just didn't allow to write equal infinity, but these days it's okay. Because in the end, the integral just simply means it's the limit work. It's not really like a real integral work. We take the limits on the integral. So it's completely okay to have, these days we revise that idea, and it's completely okay to have an equal infinity. Okay. All right. So now, along the example one that we've done with quite a few problems like that, and we picked up a couple terminologies, right? Especially it was focusing on divergence and convergence, right? Integral. And these terms never existed before until now, right? We're talking about the kind of integral where it came originally as a limit work. And so this is the definition I wrote down from yesterday, right? From the earlier lecture when we started with improper integrals here. So, see, nothing unusual, right? But now on top of these, I hope you guys still have some space that remains, because I could have mentioned that when I asked you to write down the definition. But see, when it was the integral, the improper integral where the lower end is fixed and the other end, the upper end is infinite to depth, right? Then the integral is set to be what? So if the limits, right? The limits is finite. So now at this point I've used that term so many times, but never been able to exactly explain. You probably have to wait until like a good course much later on to use that term more precisely. But finite just means when it comes to an actual number. Okay. So when your limits, if your limits, that limit working here is a finite, right? Then the integral, right? This integral I meant, right? That integral is set to be, so it's just we decide that property over here is set to be convergent. Right. Set to be convergent. Right. Simply just that, and then otherwise, the integral is. Right. We call that it's divergent. Definition. And of course, when I'm writing that in a limited board space like this, I have to skip out some of the minor details again, but you can always look it up in any of your textbook that you're using. So similarly, just this case right here, yes. If the limits, this limits working here is a finite integral convergent. Just like that, otherwise it's divergent. Because really, throughout this example, I talked about, we investigated two different kinds of improper integrals, right? One of them is the bottom end is finite, and the upper end is infinite. The other type right here, the upper end is finite, the bottom end is negative infinity. Okay. Sounds good? Okay. And so now I'm going to swing back to the other board. Okay. I'm going to promote another problem. Now let's think about, we have done this one earlier. The integral from minus infinity to 0, right? Or 1 plus x squared. You guys remember that answer? It was from it was positive pi over 2, right? And this was from the example we've done just earlier, example 1, part B. Right? So no need to reinvent the wheel, right? But I'm bringing it up here for a reason. And notice, I mentioned again that this 1 over 1 plus x squared was, as far as the graph, it looks like this, right? And the interval we were working at was from 0, right, to some point s. And then we keep letting s to infinity. And then we were looking at that half side graph. So I'm saying about the graph itself, I purposely mentioned earlier, it was continuous throughout the whole real line. So in that way, how about we do another extra problem here? It was not part of that example. How about from 0 to infinity? Okay, 0 to infinity for that 1 over 1 plus x squared. You guys at this point are familiar with double work. Why don't you guys do some independent work on this? Well, yes, we take that as just a limit works, right? T right here from t leading to infinity, 10 to infinity from 0 to t. That's exactly the same as limit work. Meaning 0 is here, we set some arbitrary interval t, right? We calculate this area or this accumulation group. Letting t keep going further out, further out. See what I mean? Go ahead, get that done, and you guys tell me what you have on that. Should be a tangent inverse again, right? Function here, the limits to positivity from this time upper end is t, right? Lower end is 0. Agree? So just that limits, same as taking the limits for tangent inverse. T, that's time minus tangent inverse 0. So what did your answer come out here? Well, that goes to 0, of course, right? So what's your answer for that? Limits. It's when t goes to positive infinity of your tangent inverse.
Pi over 2.
Pi over 2. Yes. See what I'm saying? No? So here's the thing, putting the two results here together, I mentioned again about that result from example part B, but the observation here was that from that example 1 part B, it was an integral from minus infinity to 0, right? And let me write this 0 right here. But then so same function. And then 1 over 1 plus x squared, right? And then for the other integral over here, we go from 0 to positive infinity. Right? You see how these two, the upper end limits, the upper end value of one integral is the same as the lower end, right, of the other integral that we just finished with them. But same function. And then of course, both of these throughout our work turns out to be two finite answers, right? They come out, they happen to be the same calculated value, but in the end there are two finite answers. See what I'm saying? No? And so, when we have both of these coming out finite answers, we can always add them together like that. But adding them can give me a special meaning. So adding those two finite answers like that, we can define a new, see the work. So basically it came out from two separate improper integrals. But then once both these are finite, we can define another integral, we call it minus infinity to infinity, right, on that function. So I'm saying that, hey, the way I'm seeing that, we can define this integral from minus infinity to infinity to be, right? To be just pi over 2 plus pi over 2. See what I'm saying now? Okay, so, and that's really what's just the sum of these two convergent integrals here, minus infinity to 0, right? 1 plus 1 over x squared, plus the other integral from 0 to infinity, 1 over 1 plus x squared dx. Okay. So that adding up these two convergent integrals gives rise to a third kind of improper integral for us. Okay. See what I mean? Right. So, as far as the definition, we can write it. So, part C right here, the definition, the improper integral, another improper integral over here. The improper integral, anytime you see this, like one right here, from minus infinity to infinity, right? F of x dx. That improper integral is defined to be the sum of the two other improper integrals. So minus infinity to a to infinity. Okay. Both limits, right? Exist. And of course, I'm writing that in a way of making it somehow easy to understand, but precisely speaking, you can refer to any of your text literature that you see the precise definition, the precise worded definitions for that. So I got to make it clear that this is more just like a way to represent any time you have two successful improper integrals on each two sides of that, right? Two successful convergent one, then we can add them together and we call that work. This improper integral from minus infinity to infinity. That's why a here is just some arbitrary point, right? Any point, but we call it a fixed point in your real line of numbers.